Okay, in this lecture, we want to do some numerical examples of different types of word problems that show the applications of exponential relations. They are classified under two categories, exponential growth and exponential decay. The first one, it talks about the population of a city. Initial population is 425,000 people, and the growth rate of population is announced as 1.25% per year. And we want to know what is the final population of that city after 10 years. So this is a situation where an exponential growth model is used. So we use the formula that I introduced before. We are going to substitute for p sub 0 initial population. So that's 425,000. And the growth rate of the population is 1.25%, which we have to express it as a decimal. So as a decimal, it's going to be 1.25%, which is 0.0125. Okay, so 0.0125 is what I write for R. And we want to know the population after 10 years. So the exponent is 10. So here, we just need to use a calculator to figure this out. 425,000 times 1.0125 raised to the exponent of 10 using a calculator, which I'm sure you have, it would be 481,215.1, but since we can't have 0.1 of a person, we have to round it to the nearest person. So we're going to say 481,215 people. That's the unit of measurement. In case of word problems, as you already know very well, you have to write a final closing statement, a paraphrase to actually answer the question involved in the word problem. By default, we always do that. So initial population was 425,000, but now it has grown to a higher number of 481,215 people. We are assuming that over the next 10 years, that growth rate of 1.25% does not change, of course. That's the assumption we have made here. This is one example of an exponential growth problem. Another example here is in a biology lab. We have 5,000 cells, and the doubling period of these cells is 24 hours. So that means that every 24 hours they double. And we want to know how many cells will there be in that culture after 1 week. Okay. The formula is the doubling period formula we use. And I'm going to substitute 5,000 for n sub 0, which is the initial number of cells. The base of the power is 2. The exponent is t, which is the time elapsed, but it says 1 week. Now, you know that 1 week is 7 days. And 7 days would be 7 times 24 hours, basically. Right? We can even work this out. 28 to 168 hours. That will be the time elapsed. So 1 week is equivalent to 168 hours. So when you're substituting numbers in this fraction, the numerator and the denominator must have the same unit of measurement. So I go 168 over 24, and that will be the exponent I'm going to substitute for the base of 2. So 5,000 times 2 to the exponent of 168 over 24. The top is in hours, bottom is also in hours. Or you can have both numerator and denominator expressed as in days, for example, or minutes or seconds. As long as both top and bottom have the same unit of measurement, that is what counts. Now, again, using the calculator and using the power key button, we find out the answer is 640,000 cells. So this tells us that if we begin with 5,000 cells, we will end up with 640,000 cells only after 7 days passing by, on condition that the doubling period of this particular cell happens to be 24 hours. This is another example of an exponential growth situation. A third one is here. This one is about the price of a house, or the value of the house. Today is $945,000. It's almost $1 million. And the growth rate, the rate with which the house prices have gone up, we are assuming that to be 5% per year. And we want to know what the price of this house was 20 years ago. Okay, so 20 years ago, there was a house, and this was worth like X dollars or something, we don't know. But over the 20 years, up to now, it has appreciated in value. And now, with the assumption of 5% growth rate per year, the price has become $945,000. But we want to figure out how much is or was this house worth 20 years ago. So this is an example of appreciation of assets. So the price now, which is the final price, final value, is 945,000. Initial price or initial value of the house, we don't know. That's V sub 0. We need to find it. And the rate is 5% expressed as a decimal with 0.05. And the exponent is 20 that we plug in for n because we want to know how much this house was worth 20 years ago. So doing the math here, we have 1.05 raised to the exponent of 20 times V naught is 945,000. So clearly we have to divide both sides by this power on the right in order to solve for V sub 0. So V sub 0 becomes 945,000 divided by 1.05 to the exponent of 20, because these two cancel out each other on the right hand side. And we end up with an answer that is, using a calculator of course, 356,160.56 cents. So about 360,000 basically. The unit of measurement is dollars. So we see that the price of the house was relatively cheap 20 years ago. It was only $356,000, which it's barely you can find a house with that price nowadays. So the price was $356,000, but then with that growth rate of 5% over the period of 20 years, now it has grown up to this bigger price of $945,000. Another example of exponential growth, appreciation of assets in this case. Next one, it's about exponential decay. We have 40 kilograms of some sort of radioactive substance, okay? It could be radium, it could be strontium, it could be any kind of chemical radioactive element. 40 kilograms. And H here stands for half-life, okay? So H is the half-life, and we said that half-life is that time period required for a radioactive substance to decay to half of its original mass. So it has to take, it will take 5,700 years for 1 kilogram of this substance to decay to half a kilogram, basically. That's the half-life, 5,700 years. But we have 40 kilograms of this substance, and we want to know what the mass, final mass, will be, what will be the remaining mass after 25 years pass by, 25,000 years, okay? So we are going to use the half-life formula. We're going to write down m equals m sub 0, 2 to the exponent of negative t over h. The exponent is negative, as you notice. So I plug in 40 for m sub 0, and then the exponent is negative 25,000 divided by h, half-life, which is 5,700. So the numerator 25,000, the denominator 5,700. The exponent is negative, and we are multiplying 40 by this power with the negative exponent. Or you could have written 1/2 instead of 2, and then the exponent would be positive, as I said before. So now, using a calculator, we are going to find the remaining mass of this radioactive substance. 1.913 kilograms is how much will be left. Obviously, 25,000 years is a long period of time, and that 40 kilogram, after 5,700 years, it becomes 20 kilograms. And then after another 5,700 years pass by, that 20 kilogram becomes 10 kilogram. And then that 10 kilogram becomes half of it, which is 5 kilograms. And then 5 kilograms becomes 2.5 kilograms. And just like that, it decays. And after 25,000 years, that 40 kilogram of initial mass becomes only 1.913 kilograms. Roughly, you can say approximately it's 1.9 kilograms or close to 2 kilograms. That's the mass. I repeat, in word problems, you always write a final closing statement at the very end, including the unit of measurement involved in the question. This is another example of exponential decay. It is about depreciation of assets. You buy a car. Initial value, V sub 0, is $42,000. You go to the dealership, you want to buy the brand new car, they tell you the price is $42,000. Okay, you buy the car, you drive the car for many years, you go to different cities, you travel, commute to work, whatever. 12 years pass by, and then you decide to sell the car. Okay, you go to the dealer, you say, hey, this is the car I bought you many years ago. I paid you $40,000. Now I want to sell it. How much do you buy? Well, they look at the car and say, well, this car has become a used car. It's an old car. We are going to pay only $18,000. You start, arguing. You say, well, I paid $42,000, blah, blah. Well, it doesn't matter. It has depreciated in value, and the car is worth only $18,000 today. And then you ask them, okay, what was the depreciation rate of this car? What was the average rate of depreciation per year? Did it depreciate in value 10%, 5%, 2%, 6%? How much? And we want to find that rate of depreciation, basically. So we're going to start with the formula of V equals V sub 0, 1 minus R to the exponent of n. You notice that I didn't write 1 plus R, it's 1 minus R. R stands for decay rate. 1 minus R is the decay factor. And we have the final price, which is $18,000. Initial price was $42,000. We do the substitution. The depreciation rate R, we don't know. We want to find out, actually. And the exponent is 12, because 12 years has passed by. So here we have to divide both sides by 42,000 first. So we're going to do that, and we end up with, I think, 3/7. If you reduce the fraction, 18,000 divided by 42,000, reduce the fraction, it will be 3/7. And the right side will be 1 minus R to the exponent of 12. So we have to solve this equation. We have to solve for R. Well, what are we going to do with this 12, the exponent? How can we get rid of that too? Well, we can take the 12th root of both sides, If you have an equation like x squared equals 4, what do you do to find x? You take the square root of both sides, right? So you take the square root of left side, you take square root of right side. Because the exponent was 2, you take the square root of both sides. Now here, the exponent is 12, we take the 12th root of both sides, okay? Or you may raise both sides to the exponent of 1/12. In other words, it's the same thing. So 1 minus R to the exponent of 12, I raise the left side to the exponent of 1/12, and I raise the right side to the exponent of 1/12. So using the exponent laws that we have learned and we have mastered, actually, you multiply the exponents, it becomes 1. So we have 1 minus R equals 3/7 to the exponent of 1/12, which is the same as 12th root of 3/7, basically. So solving for R, we get 1 minus 3/7 to the exponent of 1/12, or we can say the 12th root of the fraction 3/7, and using the calculator clearly, the answer is 0.068 as a decimal. Converted into percent by multiplying by 100, the answer becomes 6.8%. So that's per year. So depreciation rate per year is 6.8% for this vehicle that you bought it 12 years ago. It was $42,000. now it's $18,000. So on average, every year it has depreciated in value by 6.8% per year. Okay, and this is just another example of exponential decay, or in particular, depreciation of assets. So I gave you 5 different examples of different applications of word problems with regards to exponential relations, and I hope you're going to read the solved examples in the textbook. You're going to practice, and you're going to do some questions to become better and better at solving word problems in this unit. Thank you very much for your attention, and have a great day.